presentation, right? We have the presentation, so you guys have to send the presentation slide to me and the TA submission. And the first week, okay, and first week of December. Okay, so probably we will having you guys present at the first or the second week. Yeah, we probably need 2 to 3 times to finish all the class. Okay, so we have another 2 chapters. Today we will go into the chapter 7. So probably we can finish our all the chapter before the second week of December. So please send the slide. So you just need to provide me the slide, okay, PPT slide. You don't need to rebuild the whole file. You need to rebuild the whole file. And then no limitation page number. No limitation on the page. You can give me 1 slide. If you can give all the information, good information, making the people, students very interested to your first only 1 slide. And that's best. Okay. So just depends on you. Okay, just depends on you. Okay. So usually, yeah, for my case, 1 minute, 1 slide for my case. But for you guys, okay, no limitation. You don't need to say, for instance, I give you 100 slides. Is that my scope will be higher? No. Yeah, it's just very important is that you have to provide good organization of the slide and good presentation of you guys for all the audience interested to your talk. Okay, and then I want to everyone have some interaction. Okay, so you guys ask the question to the presenter. Okay, and then I will give you guys bonus. So be aware that if you cannot answer, do not ask the people, okay, don't ask the question to me if I cannot answer. No need to do that, because if you cannot answer, it's okay. Yeah, it's okay. It depends, because this is open-minded to fully discuss. Okay, so this is also including in our class, okay, in our course. Okay, and then regarding the topic, okay, the topic is something relative to the materials or systems, energy materials, energy systems. You can talk about some of the electronics, solid state electronics, something relative to the energy topic, something like that. Okay, so it is a very worldwide, very high spectrum. Okay, very wide spectrum. Okay, wide spectrum. So there is no limitation of the topic. Okay, something relative to the materials and energy. Okay. So now let's talk about regarding the parameters. Okay, we have discussed about the time. Okay, so you can see this is the promotion of the electron to the conduction band to the normal band. So this is the every 50 to 1.7 per second. Okay. And in recombination, you can see, fortunately, recombination from here to here is quite low, right? Quite low. So that would be safe, right? And from here to here, to the from the conduction band to the normal homo band of the dye is between nano to millisecond. So nanosecond is still faster. Nanosecond is still faster, so you have to be very careful because it is very close. But if you can do precisely design, it can be maybe millisecond. So if 15 femtosecond provide electron, and then just millisecond, 1 electron we combine, every millisecond we combine to here. And then that's still faster, right? Do you understand? Which means that you have 9 order highest, right? 9 order highest transfer. from here to here, right? But in millisecond, it's just every 1 millisecond, for example, you compare. So still is the best. So as you can see right here, the electron injection is in this picosecond. Electron injection in picosecond, right? It's quite fast. Dye regeneration is still quite fast, right? So very short. And then the critical point is right here. Green color for the electron transfer is right here. Interfacial recombination, if we position to here, and then that's still safe. But if the interfacial recombination is close to the electron transfer, and then that will be very critical. Don't understand what I mean, right? So we have to make it electron transfer faster than electron recombination at the interface, right? So that's very critical, okay, very critical. So look about that. So backward reaction and forward reaction is right here. So we want to make it a forward reaction. It's not backward reaction. Backward reaction will pull. So one concern is also regarding the diffusion length. Here, diffusion length L is equal to D diffusivity multiplied by this tau. Tau, do you remember last time we have derived about relaxation time, right? Relaxation time, so-called the electron lifetime, right? Electron lifetime. Diffusivity, that means the material's diffusivity, right? Material diffusivity multiplied by the electron lifetime. So therefore you can get the diffusion length, right? Diffusion length. So if you have the higher diffusivity of the materials, you get the longer diffusion length. Alternatively, if you have the longer electron lifetime, you still can get the longer diffusion length, right? So why do we want to do longer diffusion length? Why? Just like everybody want to have, you want to have a longer lifetime, right? You want can survive in the world for 100 years, right? I don't want to do 100 years, too long. Should be healthy. If you're healthy 100 years, that's good. If you're not healthy for 100 years in the world, that's not good. That's bad. Right? Just curious. Okay. So let's determine if an electron has a longer lifetime, that means it can diffuse longer. So therefore, this is determined about the thickness. Because previously I didn't mention about how thicker of the TR2 same thing should we need to do, right? I didn't mention about that. So you cannot say, oh, here, Professor, you just mentioned about the TR2 nanoparticle, right? There's a high surface to volume ratio, that means we can provide more charge transfer, right? So therefore, if I can deposit the thicker film, maybe 10 micron, 20 micron, 50 micron, that's good, right? Because it provide a huge electron transfer. No, there is a limitation of the very controlling state, I would say, the electron lifetime. Okay. Because the electron lifetime can determine to the diffusion length. This diffusion length can be determined about how long of how thick of the TR2 thin film that we deposit on the TR2 on the convective glass would be best for us. Okay. So usually it is 10 to 20 micron. Okay. This is based on the diffusivity of the TR2. Because the diffusivity of the TR2 you cannot change, right? This is already fixed. Okay, there's one material has one material's its own diffusivity. Okay, so That's we already talked about this in the competition. Okay. So this is the electron lifetime and then electron diffusion coefficient, so-called diffusivity in the TL2. Okay. This is diffusivity in the TL2. So if you look about this table, you can see. Okay. Let's look about the bottom side. TL2 nanoparticle. Electron diffusion coefficient of TL2 is about 10 times minus 4 diffusivity. Okay? And then lifetime in general lifetime, but in case of the materials being designed very poor, the lifetime is very poor. But if in general, the TL2 you design is that's a high crystallinity, then probably you can have in 20 microsecond. Okay, 20 microsecond. And then you can calculate because error. You have error equal to D multiplied by tau, right? So you have the D, you have tau, right? So you can calculate about the length, right? So this length, total length could be approximately to 30 micron, which means you can deposit to the 30 micrometer. Okay, 30 micrometer. Okay, diffusion length. But usually you have to reduce to 20 microsecond, 20 micrometer. Do you know why? This is because that when the electron transfer to the TL to the conduction band to the FTO glass, it is not straight. This has a irregular route, right? So the total length is should be shorter. Okay, should be shorter. So you cannot deposit too thick, right? If you deposit, for example, you told me, Professor, because we already count 30 micron, so I can deposit 30 micron, right? If you deposit 30 micron, that means electron transfer 30 from here to here to here, maybe over than 30 micron, right? Total length, right? Because total length is not directly. There is a rule, irregular, right? Irregular route. So total length is not superhighway, something like that. Okay, it's not superhighway. It's an irregular route. So you have to reduce the thickness to approximate to 20 micron. Okay, and then for highly doped silicon, okay, this is the calculation. Okay, 100 micron, approximately 100 micron. Okay, this is the thickness. Okay, but now this is previously record. Now the thickness of the silicon can be thinner, but silicon solar cell cannot be too thin, right? 100 micron. If you can produce 50 micron, still you have a high efficiency, right? Because it is determined by the PN junction. So you don't need to having such a silicon. You can provide 10 micron. Still you can have, because it is just on the surface, right? But this is because of the technology issue. If you produce the 10 micrometer of the wafer, it becomes very brittle. Once you pick it and then break, right? When it is very brittle, right? And then too thinly, there is a bending effect. Once you use the robot to transfer, and then you will break, right? So the ductility issue, okay, mechanical issue, still need to consider. Okay, so electron diffusion coefficient, so-called diffusivity in the nanoporous TL2 is much smaller than crystallized silicon. Okay, but the recombination time is enough for 10 micron thicker electron. Okay. So the key materials for this is, as I just mentioned, dye, TL2, maybe Linux as well, and electrolyte, PT, and so on, conductivity. is a video, okay? Very simple video that you can still work in your lab, okay? Very simple, and then you can even to do such experiment in the lab. Wait a moment.
Part 1. Preparing the titanium dioxide. Part 1. Preparing the titanium dioxide suspension. Step 1. Start with 6 grams of titanium dioxide powder in a mortar and pestle. Under a pitted fume hood, slowly add vinegar in 1 milliliter increments to the solution. Grind well each time. The product will take around 30 minutes and will result in a very white, milky, paint-like solution. Step 2. Add a drop of clear dishwashing liquid to the solution, but do not grind, otherwise it will get foamy and bubbly. The dishwashing liquid will act as a surfactant, which reduces the surface tension of the solution and thus helps it coat the glass plates more evenly. Step 3. Use a funnel to pour the solution into the small dropper bottle. Leave the solution alone to equilibrate for at least 15 minutes. Part 2. Coating slides with the titanium dioxide suspension. Step 1. Clean 2 conductive glass slides by rinsing them with a wash bottle filled with ethanol. Gently dry them with a soft tissue. Step 2. Use a multimeter set to resistance, ohms, to check which side of the glass slide is conductive. The slide should conduct between 10 and 30 ohms on the conductive side and nothing on the non-conductive side. There should be a slight visible difference between the conductive and non-conductive slides as well. The conductive side will appear bluish and cloudy, while the non-conductive side will appear clear and yellowish. Step 3. Use a transparent tape to tape 1 glass slide down on the table on all 4 edges. The tape should cover roughly 1 millimeter of the slide on 3 of the edges and about 4 millimeters of the slide on the remaining edge. This tape has a controlled thickness and will form a 40 to 50 micron deep channel into which the titanium dioxide suspension can flow. Step 4. Use ethanol on a tissue to wipe off any fingerprints or oils on the slide. Step 5. Put a drop or 2 of the titanium dioxide solution on a slide and quickly spread the solution as evenly as possible over the slide using a clean glass stirring rod. Step 6. Wait for the slide to dry for a few minutes before carefully removing the tape. Part 3. Annealing the coated slides. Step 1. Anneal the titanium dioxide film on the glass slide in a fume hood or well-ventilated area. Use one of the following methods. 1. Make a simple tube furnace from a hot air gun. Start by removing the outer plastic casing at the base of the nozzle to prevent it from melting.
This hot air gun is very special. It increases the temperature to over 400 degrees. Okay, one of the hot air gun. So it can do the ambient air, the annealing process, because you prepare the titanium dioxide, and then you want to having high crystallinity, so you have to pass through the annealing process. Because for the TiO2, once you do some solvent to have the TiO2 suspension, and still on the surface there's a lot of the solvent, so therefore you have to anneal in order to make the solvent to evaporate, right? So you have to use such air gun, hot air gun to anneal it, and it can crystallize. Okay, so this kind of air gun, hot air gun can be used. Okay.
Melting. Then wrap aluminum foil around the nozzle to form an enclosed oven. The slides will lie flat inside this oven for the annealing process. Be sure to leave a small opening in the foil so that you can watch the slides for color change as they anneal. Turn the hot air gun on high or to 450 degrees Celsius. Let heat for 30 minutes. 2. Place a ring stand over an alcohol burner. Anneal the slides one by one by resting them on the ring stand at the tip of the flame for 10 minutes. Step 2. Watch the slides as they anneal. The titanium dioxide coated section should turn purplish brown, then back to white, as the heat burns off the surfactant. Step 3. Store the slides for later use. Part 4. Staining the titanium dioxide with anthocyanin dye. Step 1.
This anthocyanin dye is one of like a berry, you know, like a strawberry, blueberry. There's one kind of the dye. This is one kind of the fruit, so they grind it into the paste, solid. Okay, so and then finally they drop the TiO2. Okay, same thing to immerse the dye. So this is you can also use it as blueberry. Okay, blueberry is also one of them, or like dragon fruit. You know the dragon fruit? Is it called so-called dragon fruit? 火龙果 dragon fruit. Okay, there's some of the dye. So you can use it. Okay, this is just for the practice. Okay, for demonstration. Okay.
Use a clean mortar and pestle to crush 3 to 4 berries. Transfer the crushed berries to a petri dish. Step 2. Add about a tablespoon of distilled water to the crushed berries and stir with a clean glass rod. Step 3. Place the slide face down into the berry mixture so that the titanium dioxide coated section is submerged in berry juice. Step 4. Let the slide soak in the juice for 10 minutes. The film should be stained bright purple. If you can see any white titanium dioxide remaining on either side of the glass after 10 minutes, put the slide back into the dye for another 5 minutes. Now is a good time to start on part 4, carbon coating the counter electrode. Step 5. Lift the slide out of the juice using a pair of plastic tweezers. Rinse the slide first in distilled water to remove any fibrous debris from the berries, and then in ethanol to remove excess water from the porous titanium dioxide coated section. Glad the slide dry with a
so
tissue.
you can use the ethanol.
Step 6. You have now made a titanium dioxide dye-sensitized electrode. If the slide is not going to be used right away, store it submerged in distilled white vinegar in a closed, dark-colored bottle. Part 5. Carbon coating the counter electrode. Step 1.
The first step is using a carbon coat. Carbon coat is similar to the PT coating, right? Because carbon coat you can use like a fire to burn. Okay, so you can get the carbon to coating on the ideal glass. Okay, this is the similar to the PT catalysis because carbon also one of the catalysis.
Titanium dioxide electrode is being stained in the berry juice. Make the counter electrode from another piece of conductive glass. Step 2. Light a tea candle with a match. Step 3. Determine which side of the clean glass plate is conductive with a multimeter set to resistance, ohms. Hold the slide by one edge with the metal tongs. Pass the conductive side through the middle of the flame until the entire side is coated evenly with soot, except for where the metal tongs were. Step 4. Place the carbon-coated slide face up on the counter. Be careful, the slide will be hot. Allow it to cool. Then, use a tissue and cotton swab to clean any residual soot off the edge of the slide covered by the metal tongs to clear the carbon off a 4mm strip. This edge will be where the alligator clip attaches. Step 5. You have now made a carbon-coated counter electrode. The carbon coating on the slide is very fragile and is easily rubbed off. Be careful not to touch it. Part 6. Assembling the solar cell device. Step 1. If the stained titanium dioxide glass slide has been stored in vinegar, carefully remove it. Rinse the slide with water and then with ethanol. Then, gently blot it with a tissue. Step 2. These two slides, the titanium dioxide coated slide and the carbon coated slide, will be sandwiched together to make a solar cell. Both slides have a 4mm strip on one edge that is clear of any coating. The slides must be assembled so that the coated areas of the slides are touching each other completely. This means the slides will be offset and the 4mm empty strips will be exposed on each side. This
is because they clean this edge side, so therefore it will explore the conductive surface of the ideal, right? And then both sides face down together. So you leave this for electrode for external circuit, okay, for IV nature.
Two exposed edges will serve as the contact points for the negative and positive electrodes. Step 3. Place the dry titanium dioxide coated slide on a flat surface so that the titanium dioxide coated section is face up. Place the carbon coated slide face down on top of the titanium dioxide slide so that the coating completely covers the titanium dioxide coating, leaving a 4 mm strip exposed on each slide. Step 4. Pick up the two slides in this orientation, being careful not to let them move. Clip the edges, the ones that do not have the 4 mm strip exposed, together on both sides with 2 binder clips. Step 5. Place 1 or 2 drops of the iodide electrolyte solution at one of the edges of the slides. Step 6. Alternately open and close each side of the solar cell by releasing and returning the binder clips. The liquid is drawn into the space between the electrodes by capillary action. This wets the stained titanium dioxide film. Make sure that all of the stained area is contacted by the electrolyte. Step 7. Wipe off the excess electrolyte solution from the exposed areas of the glass using cotton swabs and tissues dampened with ethanol. The cell will not work well if there is any electrolyte solution left on the exposed areas where the alligator clips attach. Step 8. Fasten alligator clips to the 2 exposed sides or poles of the solar cell to make electrical contact to the finished device. Part 7. Measuring the electrical output. Step 1. The completed solar cell can be taken outside and measured under sunlight. The cell will last longer if it is protected from the elements by a polycarbonate plastic cover like a plastic petri dish. Sun and air will dry out the iodine electrolyte solution inside the cell, which will speed up the deterioration of the dye molecules in the berry juice. Step 2. For instructions on how to measure the voltage and amperage of the cell, see Experiment 1, Measuring Voltage and Current.
So this is the voltage output. So actually, the experiment is quite very simple to do it. Only you can still do it in your home, right? Expect you don't have the TiO2 particle. If you have the TiO2 particle, and then you just need two glass, ITO glass. So you can use the blue barrier. You can use the blue barrier as a dye, and also you can use the iodide. The iodide is the electrolyte, right? Iodide you can buy from pharmacy. You know the iodide, right? Pharmacy is the iodide. There's the same iodide solution. So this is the electrolyte. So you can do it just in your home, okay, to do something. But you don't have the hot air gun, such 400, but you can use the internal hot hair dryer maybe. Yeah, still you can do some very simple experiment. Okay, so it is quite easy to demonstration. Okay, so the TiO2 nanoparticle, this is our previous work. You can see this is the nanoparticle, most porous. Most porous, right? Most porous, that means between nanoparticle, tiny nanoparticle to the macro nanoparticle, right? That means that we want to have the particle have some space, have some voids, space, to making the light can penetrate inside of nanoparticle. So we don't want to particle too tiny. If the particle too tiny, too small, that means too dense. Too small, that means the same thing with dense, very dense. Right? Very dense, that means that the inside you have to concern the bottom layer will be hard to absorb the dye solution. And one of the concerns is the light will be hard to penetrate inside of nanoparticle. So therefore, you have to look at this. Looks like a perfect morphology. The particle size can be within 20 to 30 nanometer. If you buy from the TL2 commercialized, right now it is very easy to buy less than 10 micrometer. It is already very cheap and commercialized. For TL2 nanoparticle, you can buy very small. But we want to have a TL2 is not too small. We don't want to too small. This is 220 and 30 will be better because we can see more points. And this is the high crystallinity. You can see just like a crystalline, high crystallinity. And also, this is one of the case that because we want to have the nanoparticle can have a light scattering issue, just similar to the silicon, right? We wanted to create a textural structure. So this is the light scattering of the TL2, okay, large particle. Okay, you can see if we embed some of the large particle, okay, you can see the light can be scattering inside, right? So TL2 has an anode phase and nuclide phase. The phase transition of the TL to 200, I would say 300. Between 300 to 400, you have the phase of the anode. Okay, start to 400 degree. Okay, start to generate nuclide phase. Okay, until reach 700. 750 completely transferred to nuclide phase. So nuclide phase is a high temperature, right? So high temperature has a high crystallinity, right? High crystallinity. So this is nuclide phase. I would say you can this is R phase, this is A phase. Okay, so R phase has high crystallinity and has a light scattering. So making the light can fully scattering within the nanoparticle. So therefore can be increased charge transfer. And also this is another some of the design. This is a program there. We know that the dye is soaked on this surface, right? Dye is soaked on this surface. So light is penetrate to this side, right? Penetrate to this side. So if we have the top side, TL2, first layer, anode, second layer, nuclide. That is also possible. Previously, this slide is mixing R phase and A phase. But in this case, it's this phase, this layer is reflect, right? So if you have another layer on the, for example, you have the A phase, and you have another nuclide phase. So the light can reflect. Okay? So that will be, this will become a mirror, like a mirror. Okay. So this can improve IPC. IPC has been incident photon. IPC is incident photon. There is CCE is IPC. Sorry, I IPC is incident photon. Let me check about this. Sorry. This is the IPCE. Oh, sorry, yeah. Incident photon conversion efficiency. Okay? C is a conversion efficiency. Incident doesn't mean light incident. Okay? Photon. Okay, photon. Okay. Incident photon conversion efficiency. Usually we want to have a high IPC. Okay, IPC. This is a conversion efficiency. Here, there's right here, right? Current, sorry, not conversion, sorry. Current efficiency. Okay, current efficiency. Incident photon to current efficiency. Okay. So this is one of the solution that you can increase the IPC, okay, near the IR, okay, near IR wavelengths, okay, you can use the double layer, okay. And then actually in our previous work, we also use some of the design like nanowire, okay, nanowire. Do you understand what I mean? Nanowire is for example, what you can do is if this is a conductive layer and you grow nanowire, this is a conductive nanowire, like the ITO. What is the ITO? ITO is Indian. So, SNO2, right? There's some material that is synthesized, right? This is the conductivity, like an FTO, because we call it FTO nanowire. So, this ITO nanowire being grow on this substrate, or I would say maybe you don't need to grow, you just mix with the TL2 nanoparticle, it's still okay. So this is TL2 nanoparticle, right? So if we look at about this schematic diagram, this is the substrate, right? And you have the ITO for nanowire. And this is the substrate, right? FTO substrate. So you have the particle right here, TL2. Right? So once the electron transfer, the electron can transfer and then to the FTO, right? Right? And because here has a dye, right? Right, even dye D plus, right? So dye provides electron to here. So dye provides electron to here, and then TL2 near the FTO nanowire or YTO nanowire can transfer to here. So this is just provide a channel, right? Looks like provide a channel high speed, okay, to the TL2. Compared to this one, compared to if you just only n-test phase, and you have the nanoparticle. So electron transfer would be lower, right? You have lower, and that would remind some of the defect right here be trapped, right? If TL2 has some defect, TL2 has a lot of defect, right? It's something for the oxygen vacancy. Oxygen vacancy is positive, right? So TL2 will be trapped by oxygen vacancy, right? So you have to be very careful for this. Okay, so this is one of the design that you can mix with the ITO glass. ITO nanowire. Okay, there's some commercial, or for example, some of the like carbon nanotube, right? Carbon nanotube, graphene oxide, graphene, right? That provide the channel. So this is the design, right? FTO plus nano Y, okay? This is nano Y, okay? Just like provide the electron transfer, okay? This SEM, okay? This SEM image is taken by me, my PhD dissertation. Okay, I grow nthu-nanomaterial. Okay, I crystallinity and then deposit it. So you can see like a tree, right? Like a tree. Okay. So you can have the electron transfer more fast. Okay, so I think this is also another schematic diagram to show you of the 1, 2, 3 step. Okay, the first step is the light penetration through the TL2 photoanode. Okay, the second step is the recombination. We call the side reaction. Okay, side reaction. Okay, 3 is the recombination to the ground state. Oxidation state of the time. Okay, so S0. S0 is the ground state. S plus is oxidation state. It's an oxidation state. So charge recombination could be occur at the 1, 2, 3, okay, TL2 surface down. Okay. So this schematic diagram is similar to previous that we already mentioned. Okay. Okay, here is another design. Okay. Let me show you. Let me show you here. Or shall we take a 10 minutes break first, okay? Because I have to write something, okay? Let's take a 5 minutes, 10 minutes, okay? Then later I will show you this.